Hello, everybody. This is Aaron Schwartz, one of the secondary specialists with MCPS Public Schools. We're going to take another look at growing dots. This time, we're going to be looking at the exponential version. And again, we're going to look at expressions as summaries of patterns. In Unit 2, Topic 2, students learn to build equations recursively and explicitly as descriptions of recurring patterns. The key ideas include equations can be used as succinct descriptions of a pattern. The values of geometric sequences can be produced with an exponential function whose domain is a set of integers. The values produced by a geometric sequence is a set of discrete values. The domain and range of exponential functions are continuous over the entire domain. In previous courses, students have learned that proportional reasoning with integers and that's a skill developed in Math 6, Math 7, and IM. Students have also learned that exponents represent the number of products of the base. That's done in Math 6 and IM or Math 8. A number can be decomposed to reveal patterns. This is done extensively in elementary school and is a valuable skill that we've looked at in previous videos. We're going to be using it again today. For today, we're not going to examine the diagram. We're just going to go right to the table. Here we have a table in which at stage 1, we have 3 dots. In stage 2, we have 6. And in stage 3, we have 12. But we don't have the values completed for stage 4 and stage 5. Instructionally, this would be a good opportunity to ask students what they notice and what they observe about the values. Some students may articulate that you're adding a number to itself to get the next stage. Others may see this as multiplication, specifically a product of 2. Either way, they can develop stage 4 and stage 5, 24 and 48. Just as in previous videos, we're going to expand our table. Let's look at the numbers decomposed. That first total, 3, is just 3. Now we need to write 6 as a decomposed number, but at this point we should talk about it in terms of multiplication. So that's 3 times 2. 12 is going to be 3 times 2 times another factor of 2, and so on through the table. We now have enough to recursively define this relationship. Recursively, our first term is 3, and every subsequent term is 2 times whatever the previous term was. Let's go ahead and start developing a pattern so that we can do the explicit relationship. I'm going to expand my table and start filling in my rules. In the first case, I had 3 times no powers of 2. In the second one, I had 3 times 1 power of 2. In the third row, I had 3 times 2 powers of 2, and so on through the table. At this point, I want to draw students in to those exponents in the stage. How are they related? How do we get an exponent of 0 from stage 1? How do we get an exponent of 1 from stage 2? How do we get an exponent of 2 from stage 3? And so on. The key here is that we want students to conjecture about how we can determine the exponent at any stage. Students may pick up on the fact that the exponent is always 1 less than the stage, and the key is to get students to then articulate this as an algebraic expression. For any stage, you just subtract 1, and that's your exponent. So that the rule is 3 times 2 to the n minus 1. Explicitly, the number of products of 2 is 1 less than the stage. F of x equals 3 times the quantity, 2 to the x minus 1. The same question that we explored in the linear one, we're going to explore again today. Do we start our tables at stage 1 or at stage 0? A common question. Again, we want students to do the observation and come up with a hypothesis. Here's our previous task. Let's look at a new task. This time, at stage 0, we have a value of 5. At stage 1, 15. Stage 2, 45, and so on. Students may notice that we're increasing by a factor of 3 each time. Let's go ahead and decompose those numbers. And then, let's go ahead and build a pattern of the products. 5, 5 times 3, 5 times 3 times 3, and so on. Let's go ahead and take a look at that pattern. 5 and no products of 3, 5 and 1 product of 3, 5 and 2 products of 3. Same experience. We're going to ask students to notice the connection between the stage and the exponent. At this point, they may quickly identify that whatever the stage is the same as the exponent. So for stage n, it's 5 times 3 to the n. Now it's time to make some observations and connect them back to what we learned about linear versions of this task. Again, we're going to rewrite 3 to the n as 3 to the n minus 0. Just like when we examined the linear ones, notice that whatever our starting stage was is reflected in the exponent. When we started at stage 1, it was n minus 1. When we started at stage 0, it was n minus 0, or just n. Also take a look at our initial value. Once again, whatever our initial value is the product in front, or the lead coefficient for this exponential expression. At this point, we may ask students to do things that are very similar to tasks later on in the curriculum, such as write an expression if we had started this table at stage 3 or at stage 4, or even at -1. We want students to see that the rules that they've built apply and can be used in any situation. I hope that this video helps teachers create classrooms where students explore math, observe patterns, and develop conceptual understanding. If you have questions, comments, or have a video idea, please email me at the address below. Thank you very much, and have a good day.